next speaker is from Israel. It's Klaus, I think, no?
No.
Oh, sorry. He's going to talk about geo-electrical monitoring of soil aquifer treatment. And 6 minutes.
Okay.
Thank you.
So Klaus actually is the person that did most of the work. But I have the pleasure of presenting the work. You probably all know already about soil aquifer treatment, and in some talks before you heard about the Shaftan in Israel. Basically, we treat the wastewater of the Tel Aviv larger metropolitan area and use that later on after soil aquifer treatment for irrigation in most of the south of Israel. The problem is that we pretty much reached our infiltration capacity, and the prediction for the future is that we'll need to infiltrate way, way more water. So what we want to do is to infiltrate much larger amounts of water, but keep the same water quality, the same output water quality. So we have several challenges, and we have several solutions, and I'm going to present today one of the ideas, which is to control the infiltration. So the idea is not just to flood stop whenever needed, but just to decide on the timing of the flooding according to the actual state of the subsurface. And we're going to do that using electrical resistivity. So for those of you who are less familiar with electrical resistivity, ERT, electrical resistivity tomography, it's a very simple method. You essentially take 4 electrodes, inject current through 2 of the electrodes, measure the potential through 2 others, get back to your high school education. Remember that potential divided by current means resistivity, and you have the electrical resistivity of the subsurface. Of course, you do not do that on a single 4-electrode system. You do that a few thousands of times with different spacing of the electrodes and different location of the electrode along one transect or in 2 dimensions, and collect data. Roughly, we can collect a few thousands of measurements in about half an hour. You plug everything into some inversion scheme. I'm not going to get into the details, but essentially we compare what we measure with what we simulate in terms of electrical movement in the subsurface, and you get a map of your subsurface, a map of your electrical resistivity. In normal condition, you would also translate that into whatever you're interested. In our case, we typically look at saturation of the subsurface, so saturation of the soil. Wet means conductive or less resistive. Dry means more resistive. So back to the soil aquifer treatment, we're going to work in one of the ponds of the Shafdan facility. What we did is lined 3 transects of electrode. One is very long, almost 200 meters, and 2 others short. Every one of them 96 electrodes. We put them in a trench, but it's not really needed. We do that simply because the soil is plowed from time to time, so we want to protect our electrodes and protect the tractor that actually plows the soil. And we start taking measurements. I'm going to show results only from the short transect down here. I'm going to skip this one. And what we did is track continuously the electrical resistivity of the subsurface along several flooding events, 2 of them of 24 hours, and then 2 others that are shorter, 12 hours each, with 48 hours in between here, and only 24 hours in between these 2. So that's what we get, which is a really fancy thing. You can see from time to time water flow coming from this side, like this bluish thing. That means the pond is really wet. Just for coordinations, these are 10 meters, all measured only from the surface. And that's about 50 meters of a pond, measured really continuously. Every number that you see here is really half an hour. So it's really a practically continuous measurement of the subsurface. This is great, but nobody's really going to use that in soil aquifer treatment or in ISMAR, simply because it's expensive. To use such a system that costs a few tens of thousands of dollars, to put such a system on every pond, nobody's really going to do that. So we try to think what we can do. And we look at the raw data. So every one of those lines is actually raw measurement for only 4 electrodes. 4 electrodes is something that you can measure easily with 1 voltmeter, 1 ampere meter, and 4 wires. That's all you need. The reddish ones, the reddish lines are for electrodes that are close together with about 0.5 meter separation, and the bluish ones are for electrodes that are further away, about 10 meters separation between two electrodes. And you can see that every one of the lines behave differently. The shallow one, of course, responds faster. The bluish one responds much less. And you can even see a delay between the reddish ones here and the bluish-greenish one here, which is due to a clayish layer that is in the subsurface at about 5 or 6 meters. So we really can capture with raw data the entire behavior of the subsurface. Now, the idea is that once you calibrate your system, once you have such data, you can choose the one system, the one 4-electrode system, one 4-electrode quadrupole that really represents fully your entire basin. That's something that costs probably something like a few hundreds of dollars, nothing. So you can use one of those measurements to indicate for the operator of the system when to flood the system and when to stop the flooding. You can even use this data once you calibrate in order to create zonation of your subsurface for modeling. In this case, it's very simple zonation into 4 parameters, really empirical thing, but empirical that has some meaning. So the minimal electrical conductivity would mean simply your residual water content. The maximum would mean something like your porosity. Your time here, the time constant here, simply means the rate at which the water infiltrates into the subsurface, and this one would indicate essentially the hydraulic depth of your system. So you can get pretty good calibration of your system using such electrical data. But basically, the most important thing out of the conclusions that we have here is that you can really use raw data in order to efficiently monitor your system. With very, very simple 4-electrode, 1 voltmeter, 1 ampere meter, and a battery, you can essentially monitor your entire system. Thanks.
Thank you very much. Any questions?
It's after lunch.
Okay.